Imagine standing on the surface of Mars. The sky is not blue. It is a dusty, faded red. The sun looks smaller, weaker, as if it is already too far away to care about you. There's no wind you can breathe, no sound except the faint hum inside your suit. And in that moment, you realize something unsettling. Earth is 140 million miles away. Even at the speed of light, your voice would take minutes to reach home. No rescue mission can come quickly. No emergency return flight is waiting on a runway. If something goes wrong, you are on your own. We talk about going to Mars as if it is the next vacation destination, but the truth is far more severe. The journey to Mars may be the most irreversible decision a human being has ever made, not because return is impossible, but because survival itself is uncertain. The distance, the radiation, the fuel requirements, the psychological isolation, the physics of launch windows, all of it combines into a sobering possibility. Mars may become a one-way journey for the first people who step onto it. Tonight, we are not going to talk about science fiction. We're going to talk about physics, biology, engineering, and human limits. We are going to explore why coming back from Mars is not just difficult, it may be one of the hardest engineering challenges ever attempted. And along the way, we may discover that the greatest barrier is not technology, but the human body and mind. Let's begin with something simple. Mars is, on average, about 225 million kilometers from Earth. That distance constantly changes because both planets orbit the Sun. At their closest approach, called opposition, Mars can be about 56 million kilometers away. At their farthest, more than 400 million kilometers. Even at the closest distance, a spacecraft does not travel in a straight line. It must follow a curved path called a Hohmann transfer orbit, a fuel-efficient trajectory first calculated in 1925 by German engineer Walter Hohmann. This orbit takes about 6 to 9 months to reach Mars, depending on launch timing and propulsion system. 6 to 9 months. That is half a year trapped in a metal cylinder, exposed to deep space radiation without Earth's magnetic shield protecting you. NASA's data from the Curiosity rover's radiation assessment detector measured radiation levels during transit to Mars at about 1.8 millisieverts per day. Zeitlin et al., Science 2013. Over a 6 to 8 month journey, astronauts could receive around 0.66 sieverts total dose, nearly equal to a lifetime career exposure limit for astronauts under older NASA guidelines. And that's just the trip there. Already we see the first problem. The human body evolved under Earth's protection, a thick atmosphere and magnetic field that deflects charged solar particles and cosmic rays. In deep space, galactic cosmic rays penetrate spacecraft walls. These are high-energy particles accelerated by supernova explosions. When they pass through human tissue, they damage DNA at the molecular level. Studies on radiation exposure show increased risk of cancer, cardiovascular disease, and potential neurological decline. Some rodent studies suggest cosmic radiation may impair cognitive function and decision-making. Now, imagine making life-or-death engineering decisions on Mars with slightly impaired cognition. And we still haven't landed. Landing on Mars is not easy. Mars has enough atmosphere to create friction and heat, but not enough to fully slow down heavy spacecraft. Engineers call it the 7 minutes of terror. When Perseverance landed in 2021, it used a supersonic parachute, retro rockets, and a sky crane system. The margin of error was razor thin. Now, imagine landing not just a rover, but a crew habitat, supplies, fuel production systems, ascent vehicles. Because here is the next major issue. You cannot simply turn around and leave Mars anytime you want. Earth and Mars only align properly for return every 26 months. These are called launch windows. If astronauts miss that window, they must wait more than 2 years for the next optimal alignment. 2 years on a hostile planet. Mars's atmosphere is 95% carbon dioxide. Surface pressure is less than 1% of Earth's. Without a pressure suit, blood would begin to boil at body temperature due to low pressure, a process called ebullition. The average temperature on Mars is about minus 60 degrees Celsius. Nights near the poles can drop below minus 125 degrees Celsius. There is no breathable air, no liquid water stable on the surface, no magnetic field to protect from solar flares. A strong solar particle event could deliver a radiation dose capable of causing acute radiation sickness unless astronauts are shielded underground or inside heavily shielded habitats. Now we begin to understand something. Survival on Mars requires continuous life support systems functioning perfectly for years. And perfection in engineering does not exist. The International Space Station, only 400 kilometers above Earth, requires constant maintenance and resupply. If something breaks, astronauts can return home within hours. On Mars, spare parts would take years to arrive. Every bolt, every circuit, every oxygen generator must function reliably in dust that electrostatically clings to surfaces and infiltrates machinery. Martian dust contains perchlorates, toxic compounds that can interfere with thyroid function if inhaled or ingested. Now consider this. For a return trip, astronauts cannot carry all the fuel needed to leave Mars because it would be too heavy to transport from Earth. Instead, mission plans rely on in situ resource utilization, ISRU. NASA's MOXIE experiment aboard Perseverance successfully produced oxygen from carbon dioxide in 2021 to 2023. This was a small-scale demonstration. But scaling that up to produce enough oxygen and methane fuel for a return rocket requires massive infrastructure, chemical reactors operating continuously for months before astronauts even depart Earth. If that fuel production system fails, there is no backup gas station. This is why some mission architectures propose sending fuel production systems years in advance, ensuring return fuel is ready before humans arrive. But again, everything must work flawlessly on a planet where no human technician is present. Now let's move deeper. Even if technology functions perfectly, the human body may not. Mars's gravity is only 38% of Earth's. On the Moon, Apollo astronauts experienced muscle loss and bone density reduction after only days. On the ISS, astronauts lose 1 to 2% bone mass per month despite exercise. We do not yet know what long-term exposure to 0.38 G will do. It may not be enough to maintain cardiovascular strength. It may weaken bones to the point that returning to Earth's full gravity becomes dangerous. Imagine spending 2 years on Mars, then another 6 months in microgravity during return transit. Upon arrival, your muscles weakened, your bones fragile, your immune system altered by radiation exposure. Re-entry to Earth's full gravity might feel like being crushed by your own weight. Some researchers have proposed that early Mars settlers might physiologically adapt over generations, becoming slightly taller due to lower gravity, perhaps developing different skeletal structures. But that adaptation would not help the first generation. The first generation must survive the transition both ways. Now we step into something rarely discussed: psychology. During the Mars 500 isolation experiment, 2010 to 2011, 6 volunteers lived in a simulated spacecraft for 520 days in Moscow. Researchers observed mood fluctuations, sleep disturbances, and social tension. Even without real danger, isolation took a measurable toll. A Mars mission would include real risk, real confinement, real awareness that help is months away. Communication delay ranges from 4 to 24 minutes one way. Conversations with Earth would not be conversations, they would be recorded messages. No real-time reassurance, no immediate support. Studies in extreme isolation environments, Antarctica, submarines, and long-duration spaceflight show increased risk of depression, conflict, cognitive decline, and what psychologists call behavioral withdrawal. Now imagine receiving news from Earth: illness in the family, loss, global crisis,
and knowing you cannot return. At this point, we begin to see why the phrase one-way journey is not dramatic exaggeration. It is a statistical risk. Technology may allow return. Physics permits it, but risk accumulates. Radiation exposure during transit, radiation exposure on surface, equipment failure, fuel production failure, launch window constraints, psychological breakdown, medical emergency. On Earth, redundancy saves lives. On Mars, redundancy is limited by payload mass and cost. And here is the deeper scientific challenge. Launching from Mars requires reaching escape velocity of about 5 kilometers per second. That's lower than Earth's 11.2 kilometers, which is helpful. But building, fueling, and launching a rocket from a planet with no industrial base is unprecedented in human history. Every previous space mission launched from Earth, supported by thousands of engineers, real-time telemetry, and decades of infrastructure. A Mars ascent vehicle would rely on systems assembled remotely, maintained by astronauts in bulky suits, operating in dust storms that can last for weeks. In 2018, a global Martian dust storm shut down the Opportunity rover permanently. Solar panels became covered in dust, power dropped, communication was lost. If a dust storm reduces power to a fuel production plant, return plans may collapse. Now consider this possibility.
The first Mars missions may not be designed as permanent, but they may become permanent due to circumstance. History shows us something important. Early polar expeditions often turned into survival stories when resupply failed. The Donner Party did not plan to be stranded. Shackleton did not plan to drift for months in Antarctic ice. Exploration carries uncertainty beyond initial models. Mars magnifies that uncertainty. We often imagine Mars colonization as heroic expansion, but statistically, the first crews will be accepting a higher mortality risk than any astronauts before them. NASA estimates acceptable mission risk probabilities carefully. For Artemis missions to the Moon, the acceptable loss of crew probability is around 1 in 75. For early Mars missions, projections suggest significantly higher risk. Would society accept that? And would volunteers? Or will the first settlers knowingly accept the possibility that return is unlikely, not because it is impossible, but because the margin for failure is so thin? When we move beyond the surface-level dangers of Mars, the discussion shifts from survival to sustainability. Surviving for a few months on Mars is one problem. Remaining there long enough to prepare and execute a return is an entirely different category of challenge. Let's examine radiation more precisely. The radiation environment on Mars consists of two primary components: galactic cosmic rays, or GCRs, and solar particle events, or SPEs. Unlike short bursts from solar flares, GCRs are continuous, penetrating, and extremely difficult to shield against because of their high energy and charge. These particles include high atomic number and energy nuclei, HZE nuclei moving near relativistic speeds. When HZE particles strike spacecraft shielding, they create secondary particle cascades, essentially shrapnel at the subatomic level. Shielding can paradoxically increase exposure if not properly designed. Hydrogen-rich materials such as polyethylene or water provide better protection than aluminum because hydrogen atoms reduce secondary fragmentation. NASA's Human Research Program has modeled cumulative exposure for a typical Mars mission: transit plus 500 days surface stay plus return. Estimates range from 0.6 to 1.2 sieverts, depending on solar cycle timing. Epidemiological data from atomic bomb survivors suggests that 1 sievert increases lifetime cancer risk by approximately 5% above baseline. But cancer is not the only concern. Recent studies using animal models exposed to simulated GCR environments, NASA Space Radiation Lab and Brookhaven, indicate possible microstructural changes in brain tissue. Research published in Scientific Reports 2016 and eNeuron 2018 suggests radiation may alter synaptic integrity and impair executive function in rodents. Executive function is critical for problem solving, emotional regulation, and risk assessment,
precisely the skills required during emergencies on Mars. Now consider cumulative stressors. Radiation interacts with other physiological stress factors: disrupted circadian rhythms, isolation, altered gravity, limited diet diversity, and confined habitat air chemistry. On Earth, we study stressors independently. On Mars, they occur simultaneously. This brings us to another rarely discussed factor: immune system dysregulation. Astronaut studies aboard the International Space Station have documented reactivation of latent viruses such as Epstein-Barr and varicella-zoster during long-duration missions. Mehta et al., Frontiers in Immunology 2017. Microgravity and stress hormones appear to alter immune responses. A weakened immune system on Mars means minor infections could become serious in an environment without advanced hospital infrastructure. Which leads to the next issue: medical autonomy. On the ISS, astronauts receive real-time medical guidance from flight surgeons. On Mars, communication delay prevents that. Crew members must function as autonomous medical teams. If a crew member develops appendicitis, kidney stones, internal bleeding, or traumatic injury during EVA, surgical intervention may be required in reduced gravity in a confined habitat with limited sterilization capability. Anesthesiology in partial gravity has not been extensively studied. Fluid distribution shifts in altered gravity environments may complicate surgery. Even something as basic as blood pooling behaves differently. In microgravity, fluids shift towards the head, reducing plasma volume and altering baroreceptor reflexes. Astronauts often experience orthostatic intolerance upon return to Earth, dizziness or fainting when standing. Mars gravity is partial, not zero, but 0.38 g may still be insufficient to maintain normal cardiovascular conditioning. Long-term partial gravity data does not exist in humans.
Some theoretical models suggest that chronic exposure to reduced gravity could lead to structural heart changes, possible atrophy due to reduced workload. If so, astronauts returning to Earth's full gravity after years away may face serious cardiovascular stress. This risk compounds if radiation has already induced vascular damage. Studies indicate cosmic radiation may accelerate atherosclerosis. So we are not simply talking about getting weak, we're talking about multi-system physiological alteration. Now shift from biology to planetary physics. Mars lacks a global magnetic field. Evidence suggests it once had one billions of years ago, but its dynamo shut down. Without magnetic shielding, solar wind stripped much of its early atmosphere. Today, the thin atmosphere means micrometeoroids that would burn up on Earth can reach the surface. Habitat structures must withstand not only pressure differences, but potential high-velocity micro-impacts. Dust storms present additional complications. Unlike Earth hurricanes, Martian storms have low dynamic pressure because the atmosphere is thin. However, they can envelop the entire planet for weeks, drastically reducing sunlight. Solar power reliability becomes uncertain. Nuclear fission reactors, like NASA's proposed kilopower system, offer more consistent output, but introduce thermal management challenges and radiation shielding considerations. Energy is life on Mars. Without continuous power, oxygen generation halts, water recycling stops, temperature control fails. On Earth, blackouts are inconvenient. On Mars, they are fatal. Now consider the economics. A Mars mission is not just a scientific project, it is a geopolitical and financial undertaking requiring sustained political will across decades. If a crisis occurs on Earth, war, economic collapse, environmental catastrophe, funding priorities shift. A stranded Mars crew may depend on a civilization that itself is unstable. History provides precedent. Large exploratory programs often falter when political momentum changes. The Apollo program ended abruptly despite technical success. The Soviet lunar program collapsed after early failures. If Mars missions depend on long-term Earth support for resupply, spare components, or remote troubleshooting, geopolitical instability becomes a survival variable. This introduces a subtle but profound possibility: the risk of abandonment. Not intentional abandonment, but systemic neglect due to shifting priorities. Now let's go even deeper into propulsion constraints.
Traditional chemical propulsion requires large propellant mass fractions. To return from Mars, ascent vehicles must achieve Mars orbit and then perform trans-Earth injection burns. Some mission architectures propose pre-positioned return vehicles in orbit. Others propose fully reusable heavy-lift systems, such as SpaceX's Starship architecture, using methane and liquid oxygen produced via the Sabatier reaction. CO2 plus 4H2 equals CH4 plus 2H2O.
Hydrogen must either be brought from Earth or extracted from Martian water ice. Extraction requires mining, heating regolith, electrolysis, all energy-intensive processes. Engineering reliability must approach near perfection. A small valve malfunction in cryogenic storage could compromise the entire fuel reserve. Cryogenic propellants boil off over time. Thermal insulation on Mars faces temperature swings exceeding 100 degrees Celsius between day and night. These are not theoretical inconveniences, they are mission-critical vulnerabilities. Now let's examine time. A typical conjunction-class Mars mission may require 6 to 9 months transit, about 500 days surface stay, 6 to 9 months return. Total mission duration, roughly 900 to 1100 days. Nearly 3 years. In human psychological terms, 3 years in extreme isolation exceeds most analog experiments ever conducted. Research in confined habitat simulations shows third-quarter phenomenon. Morale drops significantly after the midpoint of long missions. Conflict rates increase. Motivation declines. Add to that the knowledge that Earth grows psychologically distant. Cultural changes occur. Family members age. Political landscapes shift. Mars settlers may return to a world that feels unfamiliar. And this leads us to something rarely addressed in engineering documents: identity shift. Humans evolved with open skies, biodiversity, varied sensory environments. On Mars, visual scenery remains largely unchanged: red terrain, rocky plains, dusty horizons. Monotony has neurological consequences. Sensory deprivation studies show altered perception, time distortion, and in extreme cases, hallucinations. Architects designing Mars habitats must consider artificial lighting cycles, interior plant growth, color variation, and even virtual reality systems to maintain mental stability. But artificial environments cannot fully replicate Earth's complexity. Now we approach the philosophical boundary of biology. If long-term survival on Mars requires underground habitats for radiation shielding, settlers may rarely see the sky directly. Exposure to cosmic radiation on surface EVAs must be limited. Living underground for years alters circadian biology. Vitamin D production decreases. Mood disorders may rise without careful light spectrum engineering. Mars may require humans to live as subterranean species. And here is a critical insight. The more self-sufficient a Mars settlement becomes, the less practical returning may appear. If infrastructure, agriculture modules, and life support systems anchor settlers to Mars for survival, leaving means abandoning immense investment and possibly destabilizing those who remain. Over time, social structures may emerge that favor permanence. The first missions may not be labeled one way, but circumstances, technological fragility, physiological change, economic uncertainty, and psychological adaptation could gradually transform them into de facto one-way journeys. If the first missions to Mars are measured in years, not months, then one unavoidable question emerges: what happens if humans attempt long-term settlement? And with long-term settlement comes biology at its most fundamental level: reproduction. We have never studied human reproduction in partial gravity. In Earth gravity, nearly every developmental process is influenced. Cellular orientation, fluid distribution, skeletal formation, all are shaped by constant 1G mechanical loading. Even at the microscopic scale, cells respond to mechanical forces through mechanotransduction pathways. Proteins inside cells physically sense tension and compression. In microgravity experiments aboard the ISS, researchers have observed altered cell signaling, changes in gene expression, and modifications in embryonic development in animal models. Rodent studies have shown disruptions in sperm motility and changes in early embryogenesis under simulated microgravity conditions. But Mars is not microgravity, it is 0.38 g. That fractional gravity may be enough to partially maintain biological orientation, or it may not.
We simply do not know. If conception occurred on Mars, fetal skeletal development would take place under reduced mechanical loading. Would bone density develop differently? Would vestibular systems, the inner ear structures responsible for balance, adapt to lower gravity? If a child born on Mars later attempted to live on Earth, would their cardiovascular system tolerate full gravity? These are not speculative philosophical questions. They are measurable physiological uncertainties. Some researchers have proposed that partial gravity environments could alter gene expression epigenetically, not through DNA mutation, but through chemical markers that regulate how genes are activated. Stress hormones, radiation exposure, and altered circadian rhythms could influence long-term developmental outcomes. Now add radiation into this picture. Mars surface radiation averages around 0.2 to 0.7 millisieverts per day, depending on solar cycle activity, measured by Curiosity's RAD instrument. Over years, cumulative exposure increases. Reproductive cells, sperm and ova, are sensitive to ionizing radiation. DNA double-strand breaks in germline cells increase mutation risk. Shielding habitats underground or covering them with regolith reduces exposure significantly, but complete elimination is impossible without substantial mass. So now imagine a generation born under these conditions, a generation whose physiology has adapted to 0.38 g, whose bone density and cardiovascular structure reflect that environment, whose immune system has developed in a closed ecological system. Returning to Earth might not just be physically difficult, it could be biologically destabilizing. The phrase one-way journey begins to shift meaning. It may not only apply to the first astronauts, it may apply to their descendants. Now we approach another dimension, microbiology. Every human carries trillions of microorganisms, the human microbiome. In closed habitats, microbial ecosystems behave differently. On the ISS, studies have shown that some bacteria exhibit increased virulence and antibiotic resistance in microgravity conditions. Wilson et al. Applied in Environmental Microbiology 2007. In a Mars habitat, microbial populations will circulate in a sealed life support loop. Recycled air, recycled water, shared surfaces. Over years, microbial evolution in isolation may produce strains uniquely adapted to that artificial ecosystem. Without constant microbial exchange with Earth's biosphere, ecological diversity narrows. Closed ecosystems risk imbalance. A harmful strain could dominate. Then there is planetary protection. If humans drill beneath the Martian surface searching for water ice or potential microbial life, they risk contaminating pristine environments with Earth organisms. Forward contamination complicates scientific discovery. But there is also backward contamination. If Martian subsurface microbes exist, even extremophiles, bringing samples back to Earth carries unknown biological risk. International protocols require strict biological isolation procedures for returned samples. A crew returning from Mars would undergo extensive biological isolation. So even in success, even if astronauts return, reintegration would involve medical monitoring, quarantine, and scrutiny. Now consider the psychological implications of that. Imagine spending 3 years risking your life on another planet. You survive, you return home, and instead of celebration, you enter weeks of isolation to ensure you carry no unknown organisms. You have left Earth once, you leave it again symbolically upon return. Now let us explore atmospheric science and long-term terraforming assumptions. Some advocates suggest Mars could eventually be terraformed, thickened atmosphere, warmed surface, restored hydrological cycle. But planetary scientists like Bruce Jakowski, Nature Astronomy 2018, argue that Mars does not possess sufficient accessible CO2 reserves to create Earth-like atmospheric pressure even if all polar caps and regolith-bound carbon dioxide were released. Terraforming, if possible at all, would require technological capabilities far beyond current energy production levels, perhaps centuries of atmospheric engineering.
Therefore, the first centuries on Mars would require enclosed habitats, pressure vessels, artificial ecosystems. Closed Ecological Life Support Systems, CELSS, have been studied extensively. Biosphere 2, conducted in the early 1990s in Arizona, attempted to create a sealed, self-sustaining environment. Oxygen levels unexpectedly dropped due to microbial activity in soil absorbing oxygen and producing CO2. Crew members experienced physiological stress and food shortages. Maintaining atmospheric balance inside a sealed habitat is extraordinarily complex. Carbon dioxide scrubbing, oxygen generation, nitrogen buffering, these must remain stable indefinitely. Even small miscalculations in bioregenerative systems could produce cascading failures. Now imagine scaling this from Mars with fewer resources and greater stakes. Let's go even further into time perception and cognition. Long-duration isolation alters the brain's sense of time. Studies in polar research stations show that individuals lose accurate perception of day length and calendar progression when exposed to monotony and artificial light cycles. Mars has a 24-hour and 39-minute day, a sol, slightly longer than Earth's day. This small difference requires adjustment. Over years, circadian rhythms must entrain to this new cycle. Some astronauts have adapted successfully to Mars simulation schedules. Others struggle with sleep phase drift. Chronic sleep disruption impairs immune response, cognitive function, and emotional regulation. Add to that the absence of spontaneous novelty. On Earth, unpredictability, weather, social interaction, environmental variation stimulates neuroplasticity. On Mars, environmental predictability may induce cognitive flattening. Virtual reality environments could simulate forests, oceans, cities, but the brain recognizes artificiality. Sensory integration studies show that immersive VR reduces stress temporarily, but cannot replace multisensory real-world exposure indefinitely. Now let's examine something structural: materials fatigue. Mars experiences extreme temperature cycling. Habitat materials expand and contract daily. Over years, microfractures accumulate. Pressure vessels must maintain integrity against constant stress differentials. A slow leak in a remote habitat could go undetected until catastrophic failure. Monitoring systems must function autonomously. Redundancy requires spare materials. Spare materials increase payload mass. Increased mass increases launch cost exponentially. Physics imposes financial consequence.
And here is another reality. Rescue missions are not immediate. If a catastrophic failure occurs, Earth cannot launch instantly. Launch windows constrain response timing. Even emergency missions would require months to arrive. In practical terms, Mars crews must be entirely self-reliant. Self-reliance changes psychology. When rescue is impossible, risk perception shifts. Decision-making becomes more conservative, exploration range shrinks, innovation may slow because caution dominates. Or the opposite may happen. Fatalism may increase risk-taking behavior. Both outcomes alter mission dynamics. Now let's introduce another variable: dust toxicity. Martian regolith contains fine particles with electrostatic properties. Apollo astronauts experienced lunar hay fever due to inhalation of abrasive lunar dust. Martian dust is chemically different, containing perchlorates, reactive compounds that can interfere with thyroid hormone production and potentially damage lung tissue. Long-term, low-level exposure, even within habitats, could produce chronic health effects. So habitats must include advanced air filtration systems capable of capturing ultrafine particles without excessive energy consumption. Now consider entropy. Every closed system accumulates disorder. Filters clog, seals degrade, batteries lose capacity, software glitches accumulate. On Earth, maintenance infrastructure counters entropy. On Mars, entropy advances more quickly than resupply can compensate. Over years, the probability of critical system failure increases non-linearly, which leads to a sobering mathematical truth. The longer a mission lasts, the higher the cumulative probability of an unrecoverable failure. Even if individual systems have 99.9% reliability, multiplying dozens of such systems over thousands of days reduces overall mission survivability. This is known as system reliability compounding. Complex systems fail not because of a single dramatic flaw, but because of interacting minor faults. Mars missions will be among the most complex systems ever attempted by humanity. Now step back. We have examined radiation biology, immune suppression, cardiovascular adaptation, reproduction uncertainty, microbial evolution, ecological life support fragility, material fatigue, psychological isolation, economic instability, and compounding system failure probabilities. None of these individually guarantee that astronauts cannot return, but together they create a layered risk structure. And risk layers do not add, they multiply. This is why some space ethicists argue that early Mars missions resemble polar expeditions of the 19th century more than modern spaceflight. The explorers may not declare it a one-way mission, but history may. If we strip away the emotional and political dimensions, what remains is a question of physical limits. Limits imposed by biology, thermodynamics, radiation physics, closed-loop ecology, and propulsion efficiency. Whether a Mars mission becomes one way is not decided by ambition, but by constraints. Let's examine life support chemistry in greater detail. A human consumes roughly 0.84 kilograms of oxygen per day and produces about 1 kilogram of carbon dioxide. In a crew of 6, that is over 5 kilograms of oxygen required daily. Over 500 days on the Martian surface, that becomes more than 2,500 kilograms of oxygen, not including contingency margins. Electrolysis of water can generate oxygen, but it requires power and purified water. The reaction splits H2O into hydrogen and oxygen. Oxygen is used for breathing. Hydrogen may be recycled into methane production through the Sabatier reaction for fuel synthesis. But electrolysis systems degrade over time. Membrane fouling, electrode corrosion, catalyst poisoning all reduce efficiency. On Earth, such systems are regularly serviced. On Mars, maintenance opportunities are limited and spare components are finite. Closed-loop environmental control and life support systems, or ECLSS, on the ISS recover about 90% of water from urine and humidity condensate. Even that system has required repeated upgrades and troubleshooting over 2 decades. For Mars, recovery efficiency must exceed 95% to avoid excessive resupply mass. Achieving that level of recycling reliability for 3 years continuously without failure is unprecedented. Then there is nitrogen. Mars' atmosphere is about 2.7% nitrogen, extremely thin. Human habitats require nitrogen as a buffer gas to maintain total pressure and prevent oxygen toxicity. Extracting nitrogen from the Martian atmosphere is energy-intensive because of low atmospheric density. Without sufficient nitrogen, habitats would rely on imported reserves. If habitat pressure drops significantly due to a leak or material fatigue, nitrogen loss may not be recoverable locally at scale. Now consider thermodynamics. Heat management in space and on Mars differs dramatically from Earth. On Earth, convection carries heat away efficiently. Mars's thin atmosphere reduces convective cooling. Spacecraft and habitats must rely heavily on radiative heat transfer. Electronics, reactors, human metabolism all generate heat. In a sealed habitat, thermal imbalance can become life-threatening. Radiators exposed to dust storms may lose efficiency as dust accumulates, reducing heat rejection capability. Dust adherence is enhanced by static charge buildup. Martian dust particles are fine and jagged. Over time, they erode seals and mechanical joints. This leads to another engineering variable, tribology, the study of friction, wear, and lubrication. Lubricants behave differently in low-pressure environments. Some volatilize or degrade under radiation. Mechanical systems operating in Martian dust and temperature swings experience accelerated wear. Bearings, seals, pumps, critical life support components must function for years. Failure of a single pump in a water recycling loop could cascade into oxygen production failure. Let's now examine atmospheric entry and return trajectory constraints in more precise orbital terms.
To return from Mars, a spacecraft must perform trans-Earth injection at the correct orbital alignment. The delta-V requirement from low Mars orbit to trans-Earth trajectory is approximately 1 kilometer per second. Achieving Mars orbit from the surface requires roughly 4.1 kilometers per second, including gravity losses and aerodynamic drag. The ascent vehicle must carry propellant sufficient for both orbital insertion and injection burn. Any shortfall in fuel production on Mars means the spacecraft may reach orbit but lack energy to depart. Orbital mechanics is unforgiving. A miscalculated burn of even a few meters per second can result in missing Earth by thousands of kilometers months later. Navigation correction burns require additional propellant reserves. Guidance systems must operate autonomously with high precision due to communication delay. Now let's consider structural radiation shielding more quantitatively. Effective shielding against GCR would require approximately 20 to 30 grams per square centimeter of hydrogen-rich material to significantly reduce exposure. That equates to several tons of mass per habitat module. Using Martian regolith as shielding is feasible. Covering habitats with 2 to 3 meters of soil can reduce radiation exposure dramatically. But excavation requires heavy machinery, which requires power, maintenance, and redundancy. If shielding is insufficient during a major solar particle event, astronauts must shelter in a storm shelter, a highly shielded core area, possibly surrounded by water tanks or food supplies for additional hydrogen content. Solar particle events can deliver high doses in hours. The August 1972 solar storm, which occurred between Apollo missions, would likely have delivered a potentially lethal dose to astronauts outside Earth's magnetosphere. Mars lacks a global magnetic field, so such events pose serious acute risk. Now we move to musculoskeletal adaptation in more technical detail. Bone loss in microgravity occurs due to reduced mechanical loading, which downregulates osteoblast activity and increases osteoclast-mediated resorption. In partial gravity, modeling suggests that load-bearing may not fully stimulate bone remodeling pathways.
Countermeasures on the ISS include resistive exercise devices providing up to 600 pounds of force. Mars habitats would require similar high-load exercise systems to mitigate atrophy. However, prolonged exposure to 0.38 G may still produce structural changes not reversible upon return to 1 G. Bone microarchitecture alterations may not fully restore. Muscle fiber composition also shifts in low-load environments. Slow twitch fibers decrease, fast twitch fibers atrophy. Reconditioning after years may require extensive rehabilitation. Now, consider neurovestibular adaptation. The inner ear uses gravity as a constant reference. In altered gravity, otolith organs receive different signals. Astronauts in microgravity experience space motion sickness during adaptation. Long-term partial gravity effects are unknown. It's possible that neural recalibration occurs such that returning to Earth produces severe disequilibrium lasting months. Now let us address atmospheric escape physics and its implications for terraforming viability in more detail. Mars' escape velocity is about 5 kilometers per second, lower than Earth's 11.2 kilometers per second. Combined with low gravity and absence of magnetic shielding, atmospheric particles are more easily stripped by solar wind. Even if humans engineered a thicker atmosphere artificially, long-term retention would require replenishment or magnetic shielding technologies, perhaps artificial magnetospheres using superconducting orbital rings or plasma fields. These concepts remain theoretical and energy-intensive. Thus, Mars's natural state trends toward atmospheric loss over geological timescales. Now let's go into planetary geochemistry. Martian regolith contains perchlorate salts discovered by the Phoenix lander and confirmed by Curiosity. Perchlorates are strong oxidizers. They interfere with thyroid iodine uptake, potentially disrupting metabolism. Water extracted from Martian soil would require purification to remove perchlorates before human consumption or agricultural use. Agriculture introduces further complexity. Plants require specific light spectra, nutrient balance, and atmospheric CO2 concentration. Mars's atmosphere contains abundant CO2, but its low pressure prevents direct open-air agriculture. Greenhouses must be pressurized. Soil toxicity and lack of organic matter mean hydroponic or aeroponic systems are more practical.
But closed hydroponic systems are vulnerable to fungal or bacterial outbreaks. A pathogen affecting crop supply in a remote Mars habitat could threaten food security. Food production redundancy increases system mass and energy demand. Now, consider entropy from a statistical reliability standpoint. If a life support subsystem has a mean time between failures, or MTBF, of 5 years on Earth under controlled conditions, radiation exposure, dust infiltration, and thermal cycling on Mars may reduce MTBF significantly. If multiple subsystems operate simultaneously with independent failure probabilities, overall mission survival probability is the product of each subsystem's reliability across time.
Even with extremely high individual reliability, extended mission duration mathematically increases cumulative failure probability. This is not pessimism, it is reliability engineering. And reliability engineering is what ultimately determines whether return capability remains viable by the time launch window arrives. Finally, let's examine metabolic resource requirements numerically. A human requires roughly 2,000 to 3,000 kilocalories per day. For 6 crew members over 1,000 days, that is roughly 12 to 18 million kilocalories total. Transporting that mass from Earth is impractical. Bioregenerative agriculture must supply a substantial fraction. Crop yield per square meter under controlled LED lighting can reach high efficiency, but power demand becomes enormous. Energy production and food security become tightly coupled variables. If power output declines due to reactor malfunction or dust accumulation on solar arrays, food production may drop, which means survival and return readiness become linked to energy continuity over multi-year timescales. When you integrate all of this, radiation exposure accumulation, system reliability decay, biological adaptation uncertainty, propellant production dependence, and strict orbital windows, the phrase "may be a one-way journey" emerges not as drama but as a probabilistic assessment. Return from Mars is physically possible, but it requires that dozens of independent high-risk variables remain within acceptable margins for nearly 3 continuous years. The deeper the science goes, the narrower those margins appear. Mars is often described as cold and dry, but that simplification hides a highly dynamic and complex atmospheric system. The average surface temperature is about -60 degrees Celsius. However, that number is misleading. Near the equator during summer midday, temperatures can briefly rise above 0 degrees Celsius. At night, the same region may drop below -80 degrees Celsius. Near the poles, winter temperatures can fall below 125 degrees Celsius. This extreme thermal cycling matters because materials expand and contract daily. Metal fatigue increases, seals stiffen and crack, polymer components become brittle. On Earth, temperature variation of 40 degrees Celsius is considered extreme. On Mars, swings of 100 degrees Celsius within a single sol are common. Now consider atmospheric pressure. Mars's surface pressure averages about 6 millibars, less than 1% of Earth's 1,013 millibars. But pressure is not constant. It changes seasonally by up to 25%. Why? Because carbon dioxide, which makes up 95% of the Martian atmosphere, freezes at the poles during winter and sublimates back into gas during spring. Entire portions of the atmosphere literally freeze onto the surface. This seasonal atmospheric collapse and re-expansion alters global pressure patterns and wind dynamics. Imagine designing a habitat where external pressure fluctuates significantly over months. Structural stress loads change, airlock differential pressure gradients vary. Now let's look at wind. Mars has thin air, so wind force is weaker than on Earth at equivalent speeds. However, wind speeds can reach 60 to 100 kilometers per hour during storms. Because the air density is low, the dynamic pressure is less destructive than a terrestrial hurricane, but it is sufficient to transport fine dust globally. And dust is the defining climatic feature of Mars. Martian dust particles are extremely small, often less than 3 microns in diameter. That size allows them to remain suspended in the atmosphere for extended periods. Global dust storms occur irregularly, sometimes enveloping the entire planet for weeks or months. These events dramatically reduce surface sunlight. In 2018, one such storm reduced solar radiation enough to end the Opportunity rover mission permanently. If a Mars base depends primarily on solar arrays, a prolonged global dust storm could reduce energy production below survival thresholds. Even nuclear reactors are not immune to climate. Dust deposition on radiators can reduce heat dissipation efficiency. Reactor cooling systems rely on radiative exchange with the cold Martian sky. If radiators are coated with insulating dust, internal temperatures could rise. During dust storms, atmospheric opacity, tau value, increases dramatically. This affects not only power generation but also communication systems relying on line-of-sight optical instruments. Thermal infrared radiation trapping by airborne dust can create complex temperature inversions. While Mars lacks the dense greenhouse effect of Earth, dust temporarily increases atmospheric heat retention, slightly warming nighttime temperatures. Climate variability also affects fuel production. If methane and oxygen are produced via ISRU systems powered by solar energy, energy fluctuation during storms directly impacts propellant accumulation rates. Missing a launch window due to insufficient fuel production means waiting another 26 months. Now let's examine water in the Martian climate system. Mars has water ice at the poles and beneath the surface at mid-latitudes. Radar observations from Mars Reconnaissance Orbiter indicate subsurface ice deposits possibly accessible a few meters below ground in certain regions. However, extracting water ice requires excavation, heating, and purification. Temperature variations influence sublimation rates. If exposed to low pressure and warmer temperatures, ice transitions directly to vapor. Water management systems must prevent sublimation losses during extraction. Furthermore, water vapor in the Martian atmosphere is minimal and highly variable seasonally. Humidity cycles shift between hemispheres as CO2 freezes and sublimes. Now let's examine ultraviolet radiation. Because Mars lacks an ozone layer comparable to Earth's, ultraviolet radiation at the surface is intense. UVC and UVB radiation levels can sterilize exposed surfaces over time. For astronauts, exposure risk exists primarily during EVAs. Suit materials must resist long-term UV degradation. For potential microbial life or even agricultural systems exposed to natural light, UV radiation presents a biological hazard. Now consider atmospheric chemistry beyond carbon dioxide. Trace gases include nitrogen, about 2.7%, argon, about 1.6%, and small amounts of oxygen and carbon monoxide. Methane has been detected episodically in parts per billion concentrations, though its source remains debated, possibly geological or biological. Methane variability suggests active subsurface processes. From a climate perspective, methane is unstable in Mars's atmosphere due to photochemical breakdown. Its short lifetime implies ongoing replenishment. If subsurface geological activity releases gases, localized environmental instability could affect base site selection. Now let's move to dust electrostatics. Mars's dry environment enables static charge accumulation. Dust particles can cling to surfaces through electrostatic attraction. During dust storms, triboelectric charging increases. Electrostatic discharge events pose risk to sensitive electronics. Shielding and grounding become essential for habitat safety. Over years, dust infiltration into joints and seals increases mechanical failure probability. Now we consider atmospheric density and aerodynamic challenges. Because Mars's atmosphere is thin, aerodynamic braking during landing is limited. Large mass payloads require supersonic retropropulsion, firing engines while descending at high velocity. For return missions, ascent from Mars is easier than from Earth due to lower gravity and thin atmosphere. However, the thin atmosphere provides minimal aerodynamic stabilization during launch. Launch vehicles must be stable without relying on atmospheric lift. Climate also affects launch timing. Dust opacity can interfere with optical tracking systems and solar-powered avionics. Surface winds, though low in force, may influence small ascent vehicles during liftoff. Now let's examine planetary obliquity. Mars's axial tilt is about 25 degrees, similar to Earth's 23.5 degrees, which produces seasons.
However, Mars's orbital eccentricity is higher than Earth's. This means seasonal differences are more extreme. Southern Hemisphere summers are shorter and hotter. Northern Hemisphere summers are longer and milder. Landing site latitude determines thermal environment and energy stability. Equatorial regions offer moderate conditions and more consistent sunlight. Polar regions provide water ice but extreme cold and long periods of darkness. Site selection becomes a trade-off between resource availability and environmental stability. Climate models suggest that over millions of years, Mars's axial tilt varies more dramatically than Earth's due to lack of a stabilizing large moon. Obliquity changes may have driven ancient climate shifts. While these cycles occur over long timescales, they reveal that Mars is not climatically static. Now let's discuss atmospheric escape in real time.
NASA's MAVEN spacecraft has measured ongoing atmospheric loss driven by solar-wind interaction. During solar storms, escape rates increase significantly. While this does not immediately threaten human habitats, it demonstrates that Mars's atmosphere is not protected from solar variability. Solar maximum periods increase radiation exposure, but reduce galactic cosmic rays slightly due to solar magnetic shielding. Solar minimum increases GCR flux. Mission timing relative to the solar cycle influences radiation dose and storm frequency risk. Thus, climate, solar physics, and radiation are interlinked. Now consider long-term climate unpredictability. Mars lacks oceans to buffer temperature changes. Its atmosphere holds minimal heat capacity. Local weather can shift quickly. Dust devils form frequently, observed by rovers. While small, dust devils can clean solar panels, as happened with Spirit and Opportunity, but they can also redistribute surface material unpredictably. Climate modeling for Earth benefits from dense sensor networks. Mars has only a handful of active weather stations. Our predictive capability remains limited. Operating a permanent base in an environment where meteorological forecasting is sparse increases uncertainty. Now integrate this with previous scientific layers. A Mars return mission depends on stable multi-year energy production, predictable atmospheric and dust behavior, reliable material endurance under thermal cycling, continuous propellant generation, maintained radiation shielding integrity. Climate variability directly influences each of these. Mars does not need to be catastrophic to become one-way. It only needs to be unpredictable enough, long enough, for cumulative risk to exceed safe return thresholds. And that is the essence of planetary climate as a mission variable. Not dramatic storms, but slow, compounding environmental stress interacting with complex systems. Mars is not geologically dead. For a long time, scientists believed it was. No plate tectonics, no obvious volcanic eruptions in recent history, no active oceans. It looked frozen in time. But in 2018, NASA's InSight lander changed that assumption. InSight detected Mars quakes, hundreds of them, some small, some strong enough to measure deep interior structure. The largest recorded quakes reached magnitude 4 or greater. That tells us something important. Mars still has internal stress. Its crest shifts, its mantle transfers heat. The planet contracts slowly as it cools. Now imagine building a long-term pressurized habitat, possibly underground for radiation shielding, in a seismically active environment where we have very limited historical data. On Earth, building codes rely on centuries of earthquake statistics. On Mars, we have only a few years of seismic data. Even moderate Mars quakes could stress habitat seals, crack regolith shielding layers, or destabilize subsurface lava tubes that might otherwise serve as natural shelters. And lava tubes are scientifically fascinating. Orbital imagery has revealed large collapsed pits believed to be entrances to ancient lava tubes. Some may be hundreds of meters wide. These subsurface cavities could offer natural radiation shielding and temperature stability. Inside a lava tube, temperature variation would be much smaller than on the surface. Radiation levels would drop significantly. Micrometeoroid risk would nearly vanish. From a purely scientific survival perspective, lava tubes may be the safest long-term habitats, but there are unknowns.
Structural integrity after billions of years of thermal cycling is uncertain. Internal rockfalls could occur. Dust accumulation could alter air quality if habitats are built within them. Now let's go deeper into Martian geology. Mars has the largest volcano in the solar system, Olympus Mons, nearly 22 kilometers tall. Its size tells us something about crustal structure. Because Mars lacks plate tectonics, volcanic hotspots stayed fixed for millions of years, allowing enormous buildup. Though Olympus Mons is likely dormant, geological evidence suggests volcanic activity may have occurred as recently as a few million years ago, extremely recent in geological terms. Residual geothermal heat may still exist in localized regions. If geothermal gradients exist beneath certain areas, they could provide subsurface heat sources, useful for energy extraction or maintaining liquid water pockets underground. But geothermal activity also implies potential instability. Now consider subsurface ice. Radar mapping from orbit has revealed vast ice deposits at mid-latitudes, sometimes just meters below the surface. For a human settlement, that is both promising and dangerous. Promising because water is essential for drinking, oxygen production, agriculture, and fuel synthesis. Dangerous because ice-bearing regolith changes mechanical properties with temperature. If a habitat warms the surrounding ground, subsurface ice may sublimate, causing ground subsidence. Structures could shift, foundations could destabilize. Engineering must account for permafrost-like dynamics, but in lower gravity and different soil chemistry. Speaking of soil chemistry, let's look closely at regolith composition. Martian soil contains iron oxides, giving the planet its red color. It also contains silica, sulfur compounds, and perchlorates. Perchlorates are particularly important. Under certain conditions, perchlorates can be used to produce oxygen chemically, but they are also toxic to humans and plants. If agricultural systems use processed Martian soil, perchlorate removal becomes essential. Washing regolith requires water, a limited resource. Hydroponics bypasses soil toxicity, but increases system complexity. Now let's discuss dust storms from a fluid dynamics perspective. Mars's thin atmosphere means low Reynolds numbers in many flows, yet because of global-scale pressure gradients, storms can grow enormous. Unlike Earth hurricanes fueled by ocean heat, Martian dust storms are driven by solar heating of surface air and large-scale circulation patterns. Dust absorbs sunlight, heating the atmosphere, which increases convection, which lifts more dust, a positive feedback loop. This feedback can expand regionally into global storms. Once a global storm begins, surface visibility drops dramatically. Solar radiation reaching the surface can decline by more than 90%. For a habitat relying on solar power, that is not a temporary inconvenience, it is an existential threat unless energy storage is robust. Now let's turn toward atmospheric evolution over billions of years. Isotopic measurements show that lighter isotopes of gases are depleted relative to heavier ones, evidence that Mars lost much of its early atmosphere to space. This has implications for long-term human presence. Without active magnetic shielding, any artificially thickened atmosphere would slowly erode over geological time. That reinforces a key point. Mars is not waiting to become Earth. Its planetary physics resists Earth-like transformation. Human survival there requires constant artificial stabilization. Now we shift to something subtle but critical: time delay physics. At closest approach, radio communication delay is about 4 minutes one way. At farthest distance, about 24 minutes one way. This delay reshapes operational science. Real-time teleoperation of complex systems becomes impossible. Medical consultations are delayed. Emergency troubleshooting becomes autonomous. Autonomy requires advanced AI, robotics, and decision-making authority delegated to crew.
This autonomy increases responsibility and psychological burden. In extreme isolation studies, perceived control strongly influences mental stability. Greater autonomy can increase morale, but also stress, because mistakes cannot be corrected quickly by external support. Now consider planetary dust as a chemical reactor. Ultraviolet radiation striking dust particles may drive photochemical reactions. Some experiments suggest reactive oxygen species may form on dust surfaces under UV exposure. If such reactive species are inhaled in trace amounts over long periods, long-term respiratory effects are possible. We do not yet fully understand chronic exposure risk because no human has lived on Mars. Now let's move outward. Orbital debris and micrometeoroids. Mars's thin atmosphere does not burn up as many small meteoroids as Earth's atmosphere does. While large impacts are rare, small, high-velocity particles reach the surface more frequently. Habitat outer layers must withstand micro-impacts over years. Even a millimeter-scale puncture in a pressurized habitat can cause gradual air loss. Leak detection systems must operate continuously. Now consider temperature management in suits. Mars' surface temperature swings require suits that handle both extreme cold and internal metabolic heat. Thermal regulation systems must dissipate heat without relying heavily on convection. Radiative heat exchange dominates. Dust accumulation on suit radiators reduces efficiency. Suit degradation over multiple EVAs becomes a maintenance burden. Now let's examine gravity again, but from planetary escape dynamics.
Because Mars has lower gravity, dust particles can be lofted more easily and remain airborne longer. Reduced gravity also affects plume surface interaction during rocket launches. When launching from Mars, rocket exhaust interacts with loose regolith, potentially excavating craters and ejecting debris at high velocity. Launch pad stabilization becomes necessary, requiring construction infrastructure before the first return attempt. Now we enter a fascinating planetary science detail. Mars experiences global temperature fluctuations tied to orbital eccentricity and axial tilt over tens of thousands to millions of years, known as Milankovitch cycles, similar to Earth but more extreme. While these cycles are long-term, they show that Mars' climate is dynamically sensitive. Even in short timescales, regional weather unpredictability exists because atmospheric density is low. Small changes produce large relative variations. Now integrate all of this. Climate is not just about temperature and wind. It is about energy stability, material endurance, dust infiltration, radiation interaction, water phase stability, ground mechanics, orbital timing, solar cycle variability. Each environmental variable couples to human systems. A 3-year mission does not fail because of a dramatic cinematic disaster. It fails because small environmental stresses accumulate silently. And if return capability depends on fuel generation, structural integrity, crew health, and precise orbital timing, climate becomes one of the silent deciding factors. Let's step back billions of years. Mars was not always the frozen desert we see today. Orbital imagery shows dried river valleys, delta formations, lake beds in minerals that only form in the presence of liquid water, clays, sulfates, hydrated silica. The Perseverance rover is currently exploring Jezero Crater, once an ancient lake basin fed by a river delta. This tells us early Mars had a thicker atmosphere and warmer conditions. Climate models suggest that roughly 3.5 to 4 billion years ago, Mars may have supported episodic surface liquid water. The atmosphere was likely denser, possibly containing substantial CO2 and water vapor, creating greenhouse warming. So what happened? The leading hypothesis involves loss of the planetary magnetic field. Without a magnetic shield, solar wind gradually stripped atmospheric particles into space. MAVEN data confirms this process continues today. As atmospheric pressure declined, liquid water became unstable on the surface. It either froze or sublimated.
This history matters for future settlers. It proves that Mars is climatically fragile. Small changes in atmospheric thickness lead to large changes in surface stability. Even today, briny liquid water may temporarily exist under specific conditions, but it is transient and unstable. Now let's examine cryosphere dynamics. Subsurface ice deposits are not static blocks, they respond to temperature gradients. If a human habitat generates waste heat underground, local ice may melt or sublimate. Over time, cavities may form, structural collapse could occur. On Earth, permafrost thaw destabilizes buildings in Arctic regions. Mars presents a similar but colder analog in lower gravity. Lower gravity changes soil mechanics. The angle of repose, the steepest angle at which granular material remains stable, differs. Excavation methods must account for altered granular flow behavior. If tunnels are dug for habitat expansion, regolith cohesion properties become critical. Mars soil cohesion is influenced by electrostatic forces and cementing salts.
Engineering data is limited because we have only robotic measurements. Now, let's move into atmospheric microphysics. Dust particles in Mars' atmosphere influence nucleation processes. On Earth, water vapor condenses onto aerosols to form clouds. On Mars, CO2 can condense directly, forming high-altitude CO2 ice clouds. These clouds affect radiative balance. Their formation and dissipation influence local temperature gradients. For human bases, predicting cloud cover matters for solar energy forecasting. Now consider long-duration planetary albedo changes. Large-scale human activity, mining, construction, nuclear reactors, habitat clusters, could alter local surface reflectivity. On Earth, urban heat islands are measurable. On Mars, changes in albedo may slightly affect local microclimates. While global impact would be negligible initially, localized warming near habitats could influence subsurface ice stability. Now we step into planetary chemistry again. Regolith contains oxidizing agents formed by ultraviolet radiation interacting with surface materials. These oxidants may degrade organic materials over time. Any exposed polymers, habitat exteriors, rover components, undergo slow chemical erosion under UV bombardment. Material science becomes a survival science. Next, let's explore atmospheric electricity. Dust storms on Mars may generate electric fields through triboelectric charging. Experiments and modeling suggest electric discharges may occur within dust columns. Electrostatic charging can interfere with electronics, communication systems, and possibly suit integrity. Long-duration exposure to high static fields may influence sensor reliability. Now consider acoustic properties. Mars's thin atmosphere transmits sound differently. Sound travels slower and attenuates quickly. Recent rover recordings revealed that high-frequency sounds dampen faster than low-frequency ones. Why does this matter? Because acoustic leak detection in habitats, listening for hissing air, behaves differently in low-pressure environments. Sensors must account for altered acoustic propagation. Now let's move to atmospheric density variability. Daily pressure oscillations occur due to thermal tides. Heating and cooling cycles cause atmospheric expansion and contraction globally. These oscillations are measurable by landers. Pressure variations influence habitat stress loads and EVA planning. Now we turn to dust deposition rates. Solar panels degrade over time due to dust accumulation. On Earth, rain cleans panels. On Mars, there is no rain. Rovers survived partly because dust devils occasionally cleaned them. A permanent settlement cannot rely on chance cleaning events. Robotic brushing systems, electrostatic dust repulsion technologies, or tilting arrays must be developed. Energy storage becomes critical. During prolonged dust storms, energy reserves must last weeks. Batteries degrade over time. Lithium-ion cells lose capacity with charge cycles and radiation exposure.
Alternative storage methods, regenerative fuel cells, compressed gas storage, or even underground thermal storage must function reliably for years.
Now let's examine Mars's atmosphere in terms of aerodynamic flight. The Ingenuity helicopter demonstrated powered flight in a 1% density atmosphere. It required large rotor blades spinning at high speeds. Future aerial vehicles may assist in exploration and maintenance, but flight endurance is limited by thin air and dust interference. If an emergency arises far from base, rapid aerial evacuation may not be feasible due to low lift and power constraints. Now consider global topography. Mars has dramatic elevation differences. The northern hemisphere is lower on average than the southern highlands. Olympus Mons rises enormously above the surrounding terrain. Elevation affects atmospheric density locally. At lower elevations, like Hellas Basin, pressure is higher, slightly reducing radiation exposure and easing landing. Site selection thus becomes a multivariable optimization problem: water access, thermal stability, radiation shielding potential, landing safety, and communication visibility. Now let's move into long-term atmospheric chemistry. Photochemical reactions break down CO2 into CO and O under UV radiation. Trace oxidants form continuously. These reactive species may slowly degrade exposed metal surfaces through oxidation processes distinct from Earth rusting due to different humidity conditions. Now consider planetary night. Without thick atmosphere, heat escapes rapidly after sunset. Surface temperatures plummet. Habitats must compensate with continuous heating. Thermal inertia of regolith provides limited buffering. Power demand peaks at night, precisely when solar input is zero. Now let's shift outward: orbital debris and satellite support. A Mars base may rely on orbital communication satellites. Maintaining orbital infrastructure around Mars requires propulsion for station keeping and potential debris avoidance. Micrometeoroid flux around Mars is less studied than around Earth. If orbital assets fail, surface communication bandwidth may drop dramatically, affecting data relay and navigation. Now integrate this with solar activity. Solar cycles influence both radiation exposure and atmospheric heating rates. During solar maximum, increased solar activity can drive stronger atmospheric expansion, altering density at high altitudes. This affects aerobraking maneuvers for arriving spacecraft. Return vehicles relying on precise orbital insertion may require accurate atmospheric models to avoid undershooting or overshooting capture trajectories. Now we look at something subtle: planetary dust and human circadian biology. Dust storms can dim sunlight for extended periods. Light intensity influences melatonin production and sleep cycles. Artificial lighting inside habitats must compensate for irregular external brightness patterns. Long-term circadian misalignment affects immune health, metabolic stability, and mood regulation. Now let's move even deeper: cosmic rays secondary particle production in regolith. When high-energy galactic cosmic rays strike the Martian surface, they generate secondary neutrons that scatter upward. This creates a radiation field not only from above, but also from below. Surface radiation measurements confirm neutron backscatter contributes to total dose. Thus, shielding from overhead radiation alone is insufficient. Regolith shielding must be thick enough to attenuate secondary particle flux. Now imagine a habitat partially buried. Radiation drops significantly, but excavation disturbs soil and may increase dust infiltration. Every mitigation introduces trade-offs. Now consider atmospheric escape events triggered by solar storms. During strong coronal mass ejections, ion escape rates from Mars increase dramatically. While not immediately catastrophic, repeated events demonstrate the planet's vulnerability. Solar forecasting becomes essential for EVA scheduling and storm shelter activation. If astronauts are caught far from base during a sudden solar particle event, time to shelter becomes critical. Now let's go even further into planetary-scale electrical conductivity. Mars's dry surface and thin atmosphere allow charge separation during dust storms.
The electrical environment may influence corrosion rates and electrostatic interference with electronics. Over years, cumulative electrostatic stress may degrade sensor systems. Now integrate planetary science with mission risk modeling. Mars's climate is not extreme in the sense of hurricanes or tidal waves. It is extreme in persistence. Cold every night, radiation every day, dust every season, thermal cycling continuously. The environment does not attack dramatically, it erodes steadily. And in long-duration missions, steady erosion is more dangerous than singular catastrophe, because return capability depends on systems functioning not just at launch, but years later after relentless environmental exposure. If we follow the science to its logical conclusion, the question is no longer simply whether someone can return from Mars, but what must be built on Mars to make return possible. A return mission is not a simple reversal of departure. It requires infrastructure. On Earth, rockets launch from vast support systems, fuel refineries, manufacturing plants, supply chains, power grids, trained crews. On Mars, none of that exists. Every kilogram of hardware must survive interplanetary transit, atmospheric entry, months or years of exposure, and then perform flawlessly in an alien environment. The concept of in situ resource utilization has become central to solving this problem. Instead of bringing all return fuel from Earth, mission planners propose producing propellant on Mars itself. The atmosphere, though thin, is composed of roughly 95% carbon dioxide. Using processes such as the Sabatier reaction, carbon dioxide can be combined with hydrogen to produce methane and water. The methane could power a return rocket. The water could be electrolyzed to produce oxygen. In theory, this makes return feasible. In practice, it requires reliable reactors, continuous power, robust storage systems, and the guarantee that every component works after years of dormancy. The small experiment known as MOXIE aboard NASA's Perseverance rover demonstrated oxygen production from Martian CO2 on a small scale. It proved a principle, not a solution. Scaling that to the hundreds of tons required for a human return vehicle is a challenge of engineering magnitude. Every system would need redundancy. Every part must operate in sub-zero temperatures, low pressure, pervasive dust, and reduced gravity. Power is another constraint. Solar panels on Mars receive only about 43% of the sunlight Earth does. Dust accumulation can reduce output dramatically, as seen with previous missions that gradually lost power during storms. Nuclear reactors offer more stable output, but transporting, deploying, and shielding them introduces new layers of complexity. Then there is timing. Launch windows between Earth and Mars occur roughly every 26 months. Miss one, and astronauts must wait over 2 years before the next opportunity. That waiting period increases exposure to radiation, psychological stress, and equipment degradation. A single failed component at the wrong moment could extend a mission far beyond its planned duration.
This is where the phrase "one way" begins to acquire deeper meaning. It does not necessarily imply impossibility. It reflects the fragility of return in an environment where margin for error is thin. Earth rescues are possible because Earth is home. Mars offers no backup. And now we reach the final, quieter layer of the question, the human layer. Suppose every engineering challenge is solved. Suppose radiation shielding is adequate, propulsion reliable, fuel production successful, psychological screening effective. Suppose a return window opens exactly as planned. The question remains, what does returning mean after years on another world? Studies of long-duration isolation show that human identity adapts to environment. Astronauts who spend months aboard the International Space Station report cognitive shifts, a phenomenon sometimes called the overview effect. Seeing Earth from space alters perception of borders, conflict, and self. Now imagine the inverse perspective, looking at Earth from Mars, a small pale star rising in a salmon-colored sky. After years of confinement within a small habitat, working in 0.38 gravity, breathing recycled air, depending entirely on local systems, Mars would no longer feel alien. It would feel like home. Harsh, yes, but familiar. Earth, in contrast, would become distant not only physically but psychologically. Returning to Earth's gravity after prolonged exposure to Mars's lower gravity could require extensive rehabilitation. Bones, muscles, cardiovascular systems would struggle. Some damage may be irreversible. There is also the reality of time. A round-trip mission to Mars, even under optimistic projections, could span 3 years or more. 3 years on Earth is enough for entire life chapters to change. Families age, children grow, loved ones pass away. Social landscapes shift. The traveler returns to a world that has moved forward without them. In that sense, every interplanetary journey carries an element of one-way transformation. Even if the body returns, the person who left does not. The engineering barriers to returning from Mars are immense, but not necessarily insurmountable. Radiation can be mitigated with shielding and trajectory planning. Propellant can be manufactured locally. Psychological resilience can be strengthened through selection and training. Climate hazards can be forecasted and engineered around. But each solution adds complexity. Each layer introduces new points of failure. Mars does not forgive mistakes. So, when we say Mars may be a one-way journey, we are acknowledging something deeper than engineering difficulty. We are recognizing that Earth is uniquely equipped to sustain and rescue life, and Mars is not. We are recognizing that distance magnifies risk, and that autonomy replaces assistance. We are recognizing that exploration at its edge becomes a test of permanence. A return from Mars would represent one of the greatest achievements in human history. It would prove not only that we can travel between worlds, but that we can survive the environment of another planet long enough to leave it again. Until that infrastructure exists, until fuel plants operate reliably on alien soil, until radiation exposure is managed within safe lifetime limits, until psychological adaptation is fully understood, every Mars mission carries the shadow of asymmetry. Going is a triumph of propulsion. Coming back is a triumph of civilization. And civilization on Mars is yet to be built.